Hello, I have this very interesting infinite sum to solve for today's video. And before we start solving this problem, if you want to add this type of LaTeX expression inside the Wolfram language, you can do that in two ways. The first one is that the one I actually demonstrated here statically. So you can import LaTeX expression directly into the MaTeX function. The other way is using Inactive function so that you can just keep the original Wolfram language expression, pass this expression directly into MaTeX function, and you can convert that expression directly into LaTeX expression as well. So you can see this one almost identical to that, but with a slight algebraic modification. And the benefit of doing this is you can activate this expression to eventually evaluate this directly inside the Wolfram language interface to find actual symbolic value for the sum. And you can also convert the output into LaTeX expression as well, just passing that into the MaTeX function directly. Okay, to solve this problem, let's first expand Riemann zeta function into summation form. It simply is 1 over k to the power of s, and k is all the natural numbers. So after this conversion, we can see that the original sum of one variable, simply m from infinity, and it becomes a double sum. So you have a k direction, which k means the 2, 3, 4, 5 in the original zeta function, and you have n direction, which is correspond to the s of the powers in the original sum. Because this sum starts from n equal to 2, so actually this sum is absolutely convergent. So there is no problem to switch the order of summation. So if we look at the direct vertical direction, for example, k equal to 2, and raise the power, so these are the terms that we are going to sum first in the n direction. So for the generic case, if we replace 2 with other k's in the Riemann zeta function, the general term looks like 2 to the power of minus n times 1 over k to the power n and times 1 over n. We can combine the power terms all together and write it into a more simplified form. It's 1 over n times x to the power n, where x is simply 1 over 2k. So once we have the common term as 1 over n times x to the power of n and start about adding up for a different value of n, it's really not something strange to us. Let's first copy the code above and replace the denominator with 1 over k to the power of n. And let's evaluate the sum. Okay, we do have a term with the logarithm. And it looks like log 1 plus x or 1 minus x. So if you know how to get the Taylor series for log 1 minus x, you can use the series function inside Wolfram and choose x as the variable, set to 0, and let's expand to 10 terms. And you can see all the term looks exactly like x to the power n over n. So the next step is that you can realize we do have a term like log 2k minus 1 over log 2k. Then if we start to looking for a sum in the k direction, we do have to expand the log 2k minus 1 over 2k. And clearly, because the log of the quotient is the difference of the logs, So if we add up like in the k direction, it definitely we can cancel some of the terms using telescoping method. To show that the new double sum indeed matches with original value, so we can just evaluate using the k formula we have and comparing with the original expression. So you can see that they are exactly the same. The only difference is log 4, which is the same thing as 2 log 2. And once we have the infinity sum, if we want to explore a little more about the sum, we can actually replace the infinity part with m. It's a symbolic value. And we have the partial sum. And notice that we have harmonic numbers and gamma functions, and we don't have Euler gamma in this case. But this is very easily can be checked with asymptotic behavior of the gamma function as m approaches infinity. So if we wrap everything in the asymptotic function and the points m to infinity, we can see that the first order approximation for the quotient is square root of m. So if you collect the harmonic number part and the logarithm of the quotient of 2 gammas, which is equivalent to the square root of m, and take the limit, you have Euler gamma minus log pi again. So if you plug this number back into your partial sum and do some very simple algebra, you will have the exact same value as the highlighted values. That's it. Thank you for listening. See you next time.